Good morning, everybody. So this morning I'll present you an application case of modelization of a miniature circuit breaker remote control. So by miniature circuit breaker, we mean those small circuit breaker you have at your place and that protects your appliances. So to do that, we'll use Activate MotionSolve co-simulation and results from Flux3D. But to give you some context, let me quickly introduce you Schneider in a few words. Okay. Sorry. Okay, so Schneider Electric is the leader in digital transformation of energy management and automation, with roughly 25 billion euros yearly revenue. What does it mean? It means that with our product and solution, we help our customers manage their efficiency better, manage their energy supply better, and manage their grid better. Schneider employs roughly 150,000 people worldwide and devotes around 5% of its revenue to R&D. Oh, sorry. So, as you can see, Schneider is divided into different segment market, medium voltage, low voltage, secure power, and industrial automation. Our results are pretty well balanced all over the world, showing our global presence. And I belong to an entity called Strategy and Innovation, where we have a role of expertise for Schneider globally. That means that we support worldwide development teams, production plants, and local teams as well on any subject for all the business unit of Schneider. Now, my team is specialized, as Jim said, in electromagnetic actuator and their control strategies. Again, sorry. Here you have a few examples of products, including linear electromagnetic actuators, covering various applications. So you have small auxiliaries that are present in circuit breakers. This is typically the kind of product you have at the other end of an emergency push button. You also have remote control, like small contactors that are used for your water heating system, for example. You have low power switching, low power contactors, big contactors up to 1,600 amps, medium voltage switching, or for example, you have also actuators for short circuit protection, of course. Now, all of these products have something in common. They have a linear actuator and linked to a simple translational mechanism. And that means that we can use what I call a typical simulation model in order to be able to validate our dynamics and control strategies. So on the left side, you can recognize Activate that we've been using for a year or so. And you can see that the model is built with both Modelica blocks and control signal blocks. This is very practical, especially for electronics and mechanics, as it's always kind of a nightmare to deal with and stop in signal blocks. So in blue, you can see what we would say is the power electronic part. On this product, this is actually the model of the small contactor for heating system. Almost no electronics, just freewheel diode, the coil, of course. We also have in orange the electromagnetics. So we use results from Flux3D, and we'll see that into detail later on. In purple, we have the mechanism. And as I said, it's very simple linear mechanism with two end-stop sliding mass built with Modelica. And to take into account the resistive force, the load curve, we use just a table lookup and some friction. And of course, we have the feedback loop for the back EMF. So this model helps us cover around 80% of our applications, I'd say. And that also means that 20% of our applications are not met by this kind of model. And that's what brings us here today. So let me introduce you to the ARA IC60. This is an automatic recloser for MCBs. This is widely used in telecommunication applications, for example, antennas, or any remote location where you don't want to send a guy in an SUV every time you have a power disruption. It operates under 230 volts AC and can close up to 4 poles circuit breaker with one earth leakage protection device and 2 auxiliaries. Now, end of last year, our Chinese marketing team came to us saying like, hey guys, we have this big business opportunity, but to address it, we need remote control MCBs. So we were thinking about the ARA to address this need. So yeah, okay, it's a good idea. I mean, it's a good product. Yeah, but we need it to work for this specific market at 110 volt DC and wide voltage range. So from 77 volts to 120 volts. The load to actuate is slightly simpler. It's only 2 poles circuit breaker and 1 auxiliary, but we need to deliver the first prototypes to the customer in 4 months. So this was quite challenging. There were other scenarios, of course, but what we really need to do at the first place was to evaluate this solution and run a fast impact analysis on the main functions, software, electronics, actuator, and thermal. And in this presentation, we'll focus mainly on the actuator, because this could be quite impacting since we have only half the voltage and we don't benefit from the square root of 2 factor like in AEC. If we don't have enough power and we need to muscle up the actuator by changing the copper wire diameter, this will mean more current. And of course, this will have an impact on the electronic component sizing and on the thermal aspect as well. So with any of those other actuators, it would have been pretty simple. Often we have current regulation, so we know the electromagnetic force. There is no force conversion, it's simple translational motion, so it's really easy when looking at the static graph to see if we have enough force in the worst case in relation to the load curve, and if we have a chance to be able to close the configuration. But with the ARA, there are few specificities that makes it a little bit more tricky. So first, we have a Pwm Control Strategy. It's used to have a progressive current rise, so it allows us to close all kinds of configuration from the single pole to the big configuration we've seen before at different operating conditions, temperature, voltage, everything with kind of similar dynamics. But as you see, the actuator has a very low inductance, and there is a lot of ripple on the current that creates a dynamic effect that is not neglectable. Second thing, this is not a simple translational movement. We have a set of articulations and connecting rods, as well as a deformable part, so we don't really know the transfer function for the force, and it depends on the load. It's a little bit more complex, and at least it's complex enough for me not to be willing to describe it with 1D Modelica elements. So we needed to find a solution. What could we do? Test it. This was not an option since the electronic power supply didn't work in DC, so we would have needed to prototype the electronics, and this would have taken quite some time. So hopefully we just worked on a proof of concept with the people from Altair for the MotionSolve co-simulation with Activate. And this seemed like the perfect opportunity to put it in practice and see what it could benefit us, how it could benefit us. So let's see quickly how we build the model using Altair solutions. So the core of the model is still built within Activate. We still use Flux3D for the electromagnetics. Here you see a dashed line because we don't use co-simulation in this case. We only used response surfaces, that, as we'll see later on. Co-simulation exists. We've tested it, but in this case, I mean, most of our application, except if you want to take into account very complex phenomenon, such as eddy currents or hysteresis material, response surfaces are good enough, and it's much faster in computation time than adding a 3D finite element model into the loop. And the big difference is that we replace the 1D Modelica component by a MotionSolve model. So let's take a closer look at the model. In green, on the left, you have what we could call the software or the control strategy. It's a behavioral model that mimics the microcontroller, and we use a simple table lookup to chop down the voltage. In blue, so the power electronics, which is again a simplified model with Modelica components. So we used ideal components. In Modelica libraries, you can use more complex semiconductor models, but for this impact analysis, we didn't need to go much further into detail. So it's quite simple: a rectifier bridge, an IGBT, three-wheel diode, and the actuator. Now the electromagnetics. So as I said, we use Flux3D, so we have our separate finite element model, and that we validated before, of course. And what we do is we run a full factorial design of experiment in order to be able to obtain response surfaces for flux and force with respect to the current in the coil and to the displacement. Then we integrate it as 2D lookup tables in Activate, and we have the feedback loop for the back EMF. And now, of course, the mechanics is taken care of within MotionSolve. We only use a loop in Activate again to take into account the load curve. Probably it would have been possible to do it directly in MotionSolve, but that's the way we built the model. So now let's take a closer look to the MotionSolve model. So on the right here, you have the kinematics, just for you to better understand how the system works. So to build your model, you always start from a CAD import. You define your joints. Here we have 7 joints. We only use ideal joints, and you'll see that it's important for the rest of the presentation. We have 4 revolute joints, 1 translational joint, 2 punctual contacts. We also added springs, so preloaded spring is kind of a damping system, and return spring on the rods. Then you define your contacts. So for the contacts, what we did instead, because when you define contact between 2 parts in MotionSolve, it will mesh both geometries in order to be able to detect the contact interferences. So what we did is chop down the geometry to have a lighter model. So we'll just mesh those tiny bits, and the rest of is just for rendering. So this allows us to have a faster computation. Then you define your input forces. For us, of course, it's the electromagnetic force from the flux calculation on the mobile core of the actuator, and the resistive torque from the handle. Then you define your outputs, so you can define any outputs you want, of course, displacement, velocity, acceleration, anything you need for your analysis. Then once all of this is done, you just need to generate your coupling component. I mean, this is very easy, just set your input and outputs and it's ready to go in Activate. Just drag and drop from the library, you point towards your model on your desktop, and that's pretty much it. All of this is pretty straightforward, I'd say. It was my first experience with MotionSolve, and I didn't encounter much difficulties. The only thing where I had some troubles was in the contact parameter definitions. I'm no mechanical engineer. I didn't have any previous experience of multi-body simulation. And to have a robust model, to have a solver converge well, you need to do things the right way. And hopefully, after our troubles, the support team, Thierry, provided us with a great methodology and expertise in order to define our parameters and have an exploitable model. So now we see how it looks like in Activate, and the simulation time took 2 to 4 minutes for 100 milliseconds, which is quite okay. You can do your post-processing within Activate using the outputs you defined in MotionSolve, and of course any other signal from the system simulation model. But of course you can also do your post-processing in motion view with hyperview of hypergraph. So on the right you have your 3D model, and on the left you have some graphs. So it represents the current in the coil. On the bottom graph in red we see the displacement of the electromagnetic actuator, the core, and in blue the resistive torque. And I don't know, sorry, to launch the video just to show you how it looks like. Yeah, so this is a successful actuation at 240 volt, if I recall. So we see all the parts moving nicely. Up, yes, success. We close. So this is just for illustration. Once again, nice. So back to our problem, because we still need to answer our question. When you're lucky enough to have a product, it's always good to validate, to compare your simulation with your test results. So as I said, unfortunately, we couldn't test it in DC. Otherwise, I wouldn't have went to the trouble to build a model to answer my question. So I just ran a few quick tests in AC, so nominal voltage of today's product with the right load, and just checked the closing time. And as you can see, the initial simulation, the closing time were a bit faster than with the real products. And that's simply because, as I said, we used ideal joints. And in this product, there is quite a lot of power. So a lot of friction, some part deformation, global losses that we didn't take into account. So we didn't want to spend too much time to go into the trouble of defining for every joints, the friction parameters and everything. So what I did is simply to use a gain on the resistive torque to be able to identify the global losses and to adjust the simulation to the test. So we see with the gain tuned up, we had quite a representative model, and this allowed us to give an answer to our marketing team, saying like, okay, in nominal condition, this could work at this kind of voltage for this kind of configuration. But in the corner case, with very low voltage and very high temperature, we needed to work on the product, to modify the product and to provide a new coil. So that enlightened the situation, and he decided not to use this product for this project. But we are very happy because it allowed us, this simulation tools allowed us to provide the solution in a short amount of time. So that's pretty much it. Here are my takeaways for my first experience of co-simulation within Activate with MotionSolve and Flux. So I'd say this is really useful and efficient, and especially complementary to 1D modelization, as for us it really filled the gap. We didn't have any solution, and we are happy the way it went, and to provide this kind of insight on this kind of product. One other thing, it's very visual. By that I mean you have your 3D model, and it's easy to debug and to see if you missed something in your model definition. I don't know if you're familiar with 1D mechanism, but with Modelica, but sometimes it can be quite tricky to tune your parameters and set your initial conditions. With this, if you miss the contact and the part goes, if anything is wrong, you can see it very quickly, and it's easy to build. Then it's very easy to set up, as I said. Once you've defined your input-outputs, drag and drop in Activate. You just need to match the solver on few parameters, but that's pretty much it. And this is really, really nice things. You don't need to spend too much time on the matching the solvers, and it runs pretty smoothly. And finally, I'd like to underline the great support we had from the support team, and of course Thierry, that helped us to build these models and to improve our level of modelization in this kind of domain. And we are really looking forward to keep working this kind of way with your solutions. That's all. Thank you. And if you have any questions, I think we are late already. So